Hello, everyone. I'm very honored to have been invited to this meeting. It's a very important meeting. Unfortunately, it is not taking place in the beautiful city of Boston and Cambridge, and so we have to do it online. I'm going to share now my screen and my talk. And my talk is titled Metal Organic Framework Catalyzed Hydrodeoxygenation of Biomass to Renewable Fuels. This is part of a very broad topic that has to do with finding ways to utilize the rich biomass to generate renewable fuels, effective fuels, and to try to substitute these kinds of fuels for the petroleum-based fuels that right now are the most important source of energy. Also, the general area of this kind of green chemistry, the purpose is to reduce the carbon footprint on the planet. And so we wanted to concentrate on hydrodeoxygenation or HDO process of oxygen-rich biomass, such as, for example, very abundant cellulose or other such biomaterials, from which, with a simple reaction, one can generate alkanes, and other types of fuels that actually can be used industrially without loss of effectivity and, of course, very cheaply. The key component of this process, of the HDO process, is using heterogeneous catalyst. And so even though the reaction itself is not that complicated, even though it involves a lot of steps, but our experience in the 80s and 90s with various types of catalytic processes that were catalyzed by organometallics gives us the tools to develop catalysts that would be suitable for these types of HDO processes. And so understanding that HDO is a complex process that involves both hydrogenation, hydrogenolysis, decarbonylation, dehydration, and so it requires catalysts that are very, very versatile in their chemical makeup. And so, and when I mean versatile, it means that they can actually switch coordination sites and can adapt to the various steps of this complex reaction. And so the key thing will be the selection of the active site that is going to be critical in the effectiveness of these catalysis. And of course, we are going to concentrate on these heterogeneous catalysts because heterogeneous catalysts do not dissolve in the suspension. And so the separation of the products is relatively easy. However, we want to concentrate on several things. First of all, we would like to have the efficiency of homogeneous catalysts, in which in homogeneous catalysis you have discrete metallic complexes that are dissolved in a solution. And so each metallic center, each metallic complex constitutes a catalytic center. And so the efficiency and the selectivity is very high. And so we have to pick these two components, the chemical efficiency and the heterogeneous stability, and come up with a design that has the optimal properties of both. And so there are there's a lot of strategies to do that. The idea is the fundamental challenge is not to have the metallic or the reactive site not to have it leach from the heterogeneous environment into the solution. So to make sure there's a very strong separation between the active sites and the system itself. And so we need to look at the coordination properties of the active sites, because after all, in a catalytic process, you have to bring the various substrates, the various reactants together and facilitate their the molecular exchange to form the reaction. Another thing that we have to worry about is that under the conditions of the HDO reaction, we want to make sure that our catalyst is stable, and so we can have several turnovers, again, in order to increase efficiency of the process. So in our work, we're going to be focused on providing a potential strategy of how to design an effective catalyst in order to use in this HDO reaction. So this is the general schematic of the catalytic hydrodeoxygenation reaction. And this is a sample of we chose to use an alcohol. Of course, the substrates can be aldehydes, can be a variety of other types of oxygen-containing functional groups. Hydroxyl groups are prevalent in cellulose, for example, so we've used this type of functional group. So this kind of alcohol plus hydrogen in the presence of a catalyst will give us the alkane and water. And so this is the general process that we're going to look at. So to develop the proper catalyst, again, we would like to have a heterogeneous, that means insoluble, catalyst that has, however, discrete metallic centers. That means that it's not just a surface, a metallic surface, where you have the metals on the surface, on the top layer, that are coordinatively unsaturated. They will be the active sites, but then the second and third layer in the metallic surface are going to participate much less in the process. And so the idea to increase the exposure of metallic centers of the catalytic sites as much as possible to the substrates can be achieved by having a catalyst that is actually highly porous. And so such a multiple correlated metallic center in a single complex that are going to have homogeneous qualities being held in a heterogeneous overall complex without being tethered, but being an integral part of the complex. And so there's no leaching possible. This can be achieved by utilizing multifunctional, non-chelating. That means that if you have a ligand that has two or more functional groups at the end, it will be a rigid ligand, and so it will bond to two different metallic centers, and it's not going to self-bond to a single metallic center to form a loop. And so if we have these non-chelating rigid ligands that when coordinated to metal atoms would act as bridges and would give rise to organometallic coordination polymers. This is what it was called in the 80s and 90s, or metal organic framework, which is what it is called nowadays, with the revival of this area of chemistry. And so what we concentrated on was bidentate ligands. That means ligands that have two functional groups. With those, one can prepare organometallic polymers or coordination polymers that have the typical empirical formula of MX, LL, L being the functional group, Y, and it's a polymer, so it's a network, where Y is equal to 1, 2, or 3, M is equal to the metal, and LL represents these rigid, non-chelating, bifunctional bridging ligands. And so if if this y is equal to 1, then we're going to have a linear polymer. If y is equal to 2, we're going to have a square planar geometry and an octahedral geometry with x equals to 3. So coordination spheres are going to be according to the nature of the metal itself. And so we have looked at a variety of precursors to generate this kind of complex. And we looked at readily available metal salts or organometallic precursors such as copper nitrates, zinc nitrates, or rhodium carbonyl. And this is a transition metal. The nice things about rhodium is that usually complexes of rhodiums end up as have a square planar geometry. And so we are going to require metal-metal bonding, and if not direct metal-metal bonding, then some sort of attraction between the metal centers to form metal-metal stacking interactions. And we looked at linear rigid difunctional pi conjugated ligands. One was PDI, phenylene diazocyanide, and BDC, benzene dicarboxylate. And we see in all cases we have an extended pi system. These could be used also, our purpose was also that these are conductive ligands, and so we're making materials that have multitude of properties, so multifunctional materials. We need materials, we need these complexes that have permanent or induced available coordination sites, and we'll see how we get that. And of course, inexpensive cost of manufacturing. So one of these examples is the copper BDC complex, and we have here a rendering of this copper BDC complex, and this is the overall reaction, where we see that we have per copper, the copper is right here, is the orange ball here in the middle. These are the oxygens from the ligand, and we start with the salt, and then we have these difunctional molecules, and then they bond, and we notice that each copper center is going to be bonded by, if we look at it three-dimensionally, by 6, it's going to be 6-fold coordinated, and so per copper, we're going to have 6/2 net number of ligands. And so this is reflected here in the stoichiometry, because each ligand, of course, is shared with the neighboring copper to form this kind of bridge. And here we have some details about the crystal structure that we get. And what we end up is that we have a one-pot synthesis. You put these things together, and it's very easy to do. This is done under air. There's no need for inert gas. These are inexpensive reagents, and this is done in DMF. And the reaction is done in a few hours, and one can have very large quantities of this material. Now, of course, this kind of geometry will be dependent on the ratio between the copper nitrate and the ligand. And so with different ratios, we can actually generate a different kind of geometry. And in this case, we can generate two-dimensional, both copper and zinc coordination polymers, or MOFs. And this is the crystal structure of the two types of complexes. I'd like us to concentrate on the copper, where we see that we always have two coppers that go together. So M is 2 of M. And they're bonded through the terminal carboxylate groups of the 4 different ligands. And then the interesting part is that the 2 empty coordination sites, after all, this is an octahedral, sort of a pseudo-octahedral geometry. At the top of these, at the top of the this coordination site, the carbonyl of the DMF is actually coordinated on both sides to each copper. So this is an important factor. Now, as we analyze a little bit more the copper complex, we see that as we heat it up from room temperature to 220 degrees, we kick off the DMF, and this is an IR. These are typical bands of DMF, and see at 220 degrees, they're gone. So essentially what we do, we eliminate, and we see this better here, we really eliminate, we see this here in this crystal structure, we eliminate the DMF from the coordination sphere of the copper to leave really a two-dimensional sheet of these materials. And indeed what we have, once the DMF is eliminated, there's a little bit, this internal cage actually is growing up a little bit. There's less electron density, so they can be, they're more swollen, so that the distance between the two coppers goes from 2.63 angstroms to 2.67. Not a big difference, but nevertheless, we see this dynamic behavior. And so once the copper complex has been evacuated, the DMF has been removed, now we can suspend these complexes, and we can resuspend in different solvents, and just to check if what we get is the original structure. And what we see that if we have the N-methylpyrrolidone that also has this carbonyl group here, the crystal structure of the new copper BDC NMP, this N-methylpyrrolidone, is very similar to the original DMF coordinated sample. But when we suspend this in ethanol, the ethanol, the coordinated ethanol complex has a structure that is very similar to the one in which there is no coordinated solvent molecule. And so we can conclude here that the ethanol is not really coordinated, but just it sits in that cavity. And this is very important when you start to do catalysis, because this implies what is available and what is not, what coordination sites are available and what are not. The next complex that we can look at is the rhodium complex. So with the rhodium complex, we have the rhodium carbonyl reacting with the PDI ligand to form the square planar, exactly like in the picture. Here's the rhodium in the middle. And here is the rendering of the arrangement of the rhodium complex sheets in the Z direction. And what we see is that we have a stacking of the rhodium atoms. And we see this is the 0, 1, 0, 0, 1 direction in the Z direction. This is the X-ray diffraction corresponding to this distance that is typical of stacking interactions. And so what we note here is that when the more solvent we have, the smaller the abundance of these stacking interactions. So we have some exfoliating, event occurring. Okay, now let's look at the catalysis, preliminary catalytic experiments with the rhodium PDI. This is the reaction. This is the phenylethyl alcohol, very abundant alcohol from biomass. And with hydrogen, the reaction is very simple. It's done under 2 atmospheres of hydrogen at 60 degrees, so very, very mild conditions. And we follow the reaction we follow the reaction by infrared. So here is the red is the alcohol and the blue is the alkane. And here we look at the oxygen stretch, and we look at the decrease of the oxygen stretch as a function of time. And since we say that absorbance is really a function of concentration, so we really plot here how the reaction proceeds. And what we note here that we have a slight induction period. Okay. And now we analyze why would we have this induction period, and probably we have this induction period because it takes some time for the solvent molecules of the solvent, this is the alcohol substrate molecules, to actually penetrate inside the layers and really by the pressure of the solvent and the molecules and the substrate molecules actually break the stacking interaction and exfoliate the layers, the 2D layers, and coordinate to the metallic center. Okay, so now, because that is something that we have to take into account, now we have irradiated the stacks by UV at 350 nanometers, and we've learned that this actually is the appropriate energy to eliminate the stacking interactions. And so we irradiate for 30 minutes prior to reaction. And then what we note is that the reaction proceeds in a different manner. Actually, it's a first order reaction without an induction period. And so this is the analysis of the kinetics. So by doing so, then we decided, okay, let's look at the following trick, okay? So let's start the reaction as previously, okay? We have the induction period. Just before the end of the induction period, we irradiate for 10 seconds. And then we follow the decrease in concentration. And then again, after 2 hours, we do that again. We irradiate for 10 seconds, and then again and again. And so basically what we're doing is we're opening and closing the layers during the reaction. And then what we note is that we have these steps that correspond to the onset of, to the place, to the time where we have the radiation. And then the rate of reaction actually changes as we irradiate. So each time we open the sheets, we help the sheets. So we help the reaction along by helping push the reactant and the solvent through the layers, by helping open the layer, by exfoliating the 2D layers and exposing the reactive sites to the reaction. So in conclusion, we see that these kinds of coordination polymers are easy to make, and they're formed by what we call template polymerization, because the ligands actually dictate the way the polymerization is going to occur. The process is inexpensive, one-step, high yield, really gram quantities or more. The coordination polymers have large molecular intrinsic porosity, which facilitate the flow of reactants and products. They're characterized by modular geometries. We can have 1D, 2D, 3D, corresponding to Y equals 2, 4, or 6 here. Okay. And the 2D sheets stack via metal-metal stacking interactions, and they generate these loosely held 3D structures that help with, that are very labile, are coordinatedly, the coordination bond is weak, and so it is very easy to intercalate the substrate at not very high pressures. And so the 2D sheets may be intercalated and exfoliated by solvent molecules, and of course, the substrate. And so this exfoliation generates coordinatively unsaturated sites on the metal that facilitates the catalytic activity. So of course, these are very promising experiments, and it is an active area of research, and we hope to provide a much more broad and in-depth extent of results, perhaps in the next meeting that is going to hopefully happen in person. I'd like to acknowledge funding from NSF, NIH, into paper science and technology that is associated with the Georgia Institute of Technology, where this work has been initiated, and my collaborators, Dr. Rosario Gerhardt, Kenneth Hardcastle, and Christina Hoffman from Georgia Tech. And with that, I thank you for your attention, and hope to see you soon. And write to me anytime. Please contact me should you have any questions or comments. Bye-bye.